Okay, by the way, Professor MZ, am I pronouncing correct?
Yes.
Also again.
Yeah. I started recording, so I just put all of you as co-hosts. Yeah, just to make
Okay.
sure. Yeah, and then we can trim it like later on. Yeah, just to.
Okay, therefore, I will start the meeting.
Do you see my do you see my screen now?
Sorry?
Do you see the screen, my slides?
Yeah, we see the screen.
Okay.
No problem.
Yeah.
So we thank Professor Boumediene, MC, for meeting us in these RKHS seminars. Actually, this semester, this is the first one. Last semester, we had Mark Shun. So today, okay, today actually will be a very long seminar, I guess, because it includes machine learning, dynamical systems, and reproducing kernel Hilbert spaces, given by our Professor Boumediene MZ, who is currently a senior scientist at the Department of Computing and Mathematical Sciences at Caltech. He is also leading the research interest group on machine learning and dynamical systems at Alan Turing Institute. His research interest is at the interface of machine learning and dynamical systems, and we will hopefully learn a lot from him today on the topic of machine learning and dynamical systems meeting in reproducing kernel Hilbert spaces. So I give the word to our professor.
Yeah. Okay. Yeah. Thank you, Omar, for the introduction, and thank you all for coming. So it's a pleasure to be back between coast to METU. So METU is one of the first universities where I started talking about this interface of machine learning and dynamical systems. I was a Marie Curie Fellow in Turkey from 2013 and to 2015. And I went, when I was there, I went to visit METU and Bilkent in, I think, 2014 or something like that. Yeah, so it's a pleasure to be back, even though it's virtual this time. So this talk is more to talk about this large interface between machine learning and dynamical systems. So I try to summarize. So I started working on this for around 2008, so about like 15 years ago. And so I'll try to summarize most of some of the results. So then and then you can stop me whenever the time is running out. So it will be two talks, so I'll be giving another talk in 3 weeks. So maybe I'll give actually another talk, like a third talk later on if there is chance. So this is joint work with all these collaborators here, and So the idea, I mean, the general context is, I mean, the main question here is how to analyze complex systems. So among the current approaches to analyze complex systems is that we have the theory of dynamical systems, and that was like axiomatized through the work of Poincaré and Lyapunov around 150 years ago in the late 1800s. And so it's a theory that allows to analyze complex systems when the model is known. So it offers non-trivial ways to analyze dynamical systems. It has the status of theory, but it is currently limited to low-dimensional models. On the other side, we have machine learning, which is concerned with algorithms that are designed to accomplish a certain task, whose performance improves with the input of more data. It allows the analysis of some very high-dimensional complex systems on the basis of data when the model is not even known. So you have the theory of dynamical systems is model-based. The machine learning is data-based. But among the limitations of machine learning is that it's mostly a set of techniques and algorithms. There are no methodologies, and the theory is still underdeveloped. So it's not clear why the algorithm work and what is their domain of applicability. So if you look at it from this point of view, I mean, it makes sense to combine between the theory of dynamical systems and machine learning in order to strengthen each other by the other one. So we'll have two directions. So machine learning for dynamical systems, where the goal is to analyze dynamical systems on the basis of observed data, rather than attempt to study them analytically. So writing down a model was done because people were interested in doing calculations by hand and prove theorems, but this led to, in a way, limiting the theory of dynamical systems. And so if we try to reformulate the main questions that in the theory of dynamical systems and look at them from the point of view of data, then I mean the boundaries will necessarily extend because machine learning is allowing to deal with high-dimensional systems. But then there is a need to see how to develop theorems based on data only and or data and models, but not model only like in the classical theory of dynamical systems. So today my talk will focus mostly on this direction. The other direction is the direction of dynamical systems for machine learning, where the goal is to analyze algorithms of machine learning using tools from the theory of dynamical systems. So here we will see algorithms themselves of machine learning as dynamical system, where time is time, not the time on the clock, but time on the computer. So this application of dynamical system theory to machine learning would allow to give solid foundations to the existing methods and understand their true potential and limits, and in view of identifying the domain of applicability of the algorithm in machine learning. So yes, I came across this interface through meeting Steve Smale in around 2008, and or in 2007 he already wrote this text in the introduction to the following book, where he said that the unification of dynamical systems and learning theory is a major problem, as I explained above. And another problem is to develop a comparative study of useful algorithms currently available and to give them to give unity to this algorithm, like where you look at algorithm and machine learning as dynamical systems and try to go deeper into that. So this is around, as I said, around this time, this is where I started thinking about this kind of problems. And so this is what we wrote, for example, back in 2012, where we said that it is easier to simulate a dynamical system and analyze the empirical data rather than attempt to study them analytically. But the mathematical theory at that time, at least, that was necessary to analyze dynamical systems on the basis of observed data was still largely undeveloped, underdeveloped. I mean, that's the as explained earlier. So that's in a way, the objective of this research program is to, in a way, reformulate the main questions in dynamical systems theory, but where we look at in a way, database the qualitative theory of dynamical systems, where we develop qualitative theory of dynamics based on data, not on models. Yeah, so so I'll try to cover probably some parts of this slide and see how it goes. So I'll talk about RKHS, but I guess many of you are already familiar with RKHS theory, so I'll probably skip some of these things here, like function approximation in RKHS. And then I'll talk about probability measures in RKHS and the MMD. So here I'll probably go quickly over it because I'm sure you are familiar with this. Then I'll go on cover the question of choosing the right Hilbert space. I mean, the right Hilbert space in the RKHS. So this is the method of kernel flows. So we developed like many versions that are for dynamical systems, including sparse kernel flows, Hausdorff metric based kernel flows. Then I'll talk about detection of critical transitions for some slow fast SDEs with application to seizure detection based on EEG. So this part, you see, this is about like learning the dynamical system. Here is about, it's no longer exactly about learning the dynamics. You have like an SDE with the critical transitions, and we want to detect. We don't necessarily want to learn the SDE, but we want to detect and possibly predict when there is a critical change. So you see, we are already moving towards the qualitative part, where you don't necessarily learn the model, but you still want to understand the qualitative behavior. Then we'll talk about approximation of center manifolds, and then a data-based version of the center manifold theorem. where again, so I remember, so our goal in a way is to develop data-based theorems in dynamical system theory, and then one of the main ones, is the center manifold theorem, but also construction of Lyapunov functions. So we look at construction of Lyapunov functions in reproducing Hilbert spaces. So I guess this is where I'll probably stop here at this half of the slides, but then we'll see how it goes. Yeah. Yeah, so the main idea here, I see like a philosophical link in a way with what people are doing in physics and quantum mechanics in particular, where the goal, I think historically they all appeared around the same time in the 30s, where people were interested, had like already complex problems that they were dealing with, but they did not have the computational power. So they were looking at mathematical tricks to be able to solve complex problems using existing methods. And so one of the tricks that they were playing with was, okay, so since our problem is complicated, let's try to solve it in a different space. So let's go to a Hilbert space where computations can be made simpler. So the idea is that you consider there is an embedding phi from Rn into H, and you map your variables x to z, and we want to perform an analysis in H, where in general, but not necessarily a linear analysis in H, and then come back to Rn. So the idea here is to simplify the analysis. So we move to a space where solving the problem becomes simpler. And the transformation phi is obtained from the kernel that defines the RKHS. So these are the embedding is based on is constructed from data, and so data in a way are used to construct the Hilbert space where computations become simpler. Yeah, so one of the common questions that I usually get is that what's the link between this work and Koopman? For people who are using Koopman methods, they usually assume that the system becomes linear in a higher dimensional space. So it's the system that is linearized. Here, no, it's different. So we are not assuming necessarily that the system is linear. So what we are assuming is that the problem is mapped into a higher dimensional system where the problem becomes easier to solve in the higher dimensional system. Again, the key is not necessarily to linearize the system. The key is really to solve the problem that you have at hand by working in different space. So we want to map the system in a different space where computations in a way become simpler. And simplicity, in general, means linear, but not only linear. So we just want to simplify. Yeah. So mathematically, appeared in the 30s as an answer to the question one: is it possible to embed a metric space into a Hilbert space? That's one of the this is how I could track the questions, but I'm sure maybe you have different point of view. And so if the metric satisfies certain conditions, so it's possible to embed a metric space into a special kind of Hilbert spaces that are called reproducing Kernel Hilbert spaces. And then RKHS have been studied quite a lot in the 50s by work like Aonjan, and then in the 60s like Schwartz. Then they died a little bit, and then they were resurrected in a sense by Wahba in the 90s, then Smail in the 2000s, and since the 2000s they have been carried over. Yeah. Yeah. So yeah, as you know, it's like before anything else, reproducing Kernel Hilbert spaces are Hilbert spaces with these two properties of reproducibility and and this denseness. So reproducing Kernel Hilbert space is a Hilbert space with a reproducing kernel whose span is dense in H. That's essentially what an RKHS is. RKHS is unique, but it's not. But the feature map is not unique. So an example of construction of the feature map. Remember, the question is that we want to embed the metric space into Hilbert space. So in a way, we are looking at decomposing KXY, which is a measure of similarity, and write it as an inner product in H. So so this is what led to what we call the canonical feature map, or Aron-Jones feature map, where KXY will write as the inner product of phi CX with phi CY. And yeah, so that's the main one of the main feature map, but it's not the only one. You can have other ways of constructing the feature maps. Examples of kernels are monomial, Gaussian, and the hyperbolic tangent. Yeah, so the RKHS, they play an important role in learning theory, where the objective is to find an unknown function f from random samples, xi, yi. So one of the first things that people do is to minimize this functional e. Then we are looking for a minimizer for such functional error. And yeah, one of the closed form of the solution is the following one. We have like f rho x is equal to this expression, but since we don't know what rho is, then we end up just discretizing the criterion. So since rho is unknown, then we cannot compute f rho, and so through discretization of E, so the empirical error is the following with regularizer, which is which contains the RKHS norm. So you have lambda times the RKHS norm. So yeah, so this minimization is taken over function from the hypothesis space. And so it admits a closed form solution, which is a fsx is equal to sum of cj kx xj. So this reminds us of the Aaron-Jones canonical feature map, so which writes as cj phi jx. And so we already see that there is linearity in the phi jx. So you see it writes sum of cj phi j. So remember the question of simplifying. So here when you do function approximation, you already have linearity in the cj in the phi j. But even with that, you already have also linearity in the CJ. So because the CJs are obtained by solving the linear system, which is also linear in the CI. So we call learning the process of approximating the unknown function f from random samples on Z. The other application is the question of change point detection in RKHS. So we consider a sequence of samples x1 to xn, and we are interested in detecting a possible change point tau, such that before tau, the samples xi follow probability distribution p, and after tau, the change point, the points, they follow probability distribution q. So and then our problem is to find the point tau where there is a change. And one of the ways that is done in for kernel methods is to map the data set in RKHS as AH, and then compute a measure of discrepancy. So here, since the goal again is to simplify the problem, and by going into an RKHS, and one of the ways of doing that is by applying using metrics that are simple to compute, and the simplest one is the mean. So the MMD really is just the difference between the means in the RKHS. When you are looking at change point detection, one of the simplest methods that one applies is to look at change in means. And here, essentially, this is about looking at the change in means in the RKHS. So this is what leads to what we call the kernel mean embedding. So you have probability measure P, you map it into H, the RKHS, and then you compute the mean in the RKHS, and that's what is called the kernel mean embedding. And the maximum mean discrepancy between two probability measures is the change between the means of this between the kernel mean embeddings of P and Q. So that's the change in means between P and Q in the RKHS. So this is what's like mu Q, mu K P minus mu K Q. Yeah, so the MMD, yeah, you can be computed directly using kernels as shown by Gaetan and collaborators. So it's not exactly a metric, it's pseudometric on distributions in the sense that it satisfies all the qualities of a metric except that property, MMD PQ is equal to 0 if and only if P is equal to Q. But it can be made transformed into a metric if by choosing a proper kernel. This is what led to introducing characteristic kernels. So for the MMD to be a metric, it is sufficient that the kernel is characteristic, and that the map mu p is injective. But luckily, many characteristic kernels so we have familiar ones. I mean, for example, the Gaussian kernel, both on compact domains and on RD, for example. I mean, that's like an example of how you look at the MMD. You have like for distribution P, another one Q. So you map into the RKHS, you compute the mean, and then you measure. So the mean, kernel mean embedding for Q is the red dot, for the P is the blue dot, and then you compute the distance, and this gives you a measure of discrepancy. And then when you map it back to Rn, to R here in this case, then you get yeah, the MMD is going to be the red one. So yeah, so you get the maximum. Yeah, sorry, the green. So blue and red, and then the green. So you see this is where the change is happening. Yeah, another property, interesting property of the characteristic kernel is that the MMD metrizes the weak star topology on probability measures, in the sense that if the MMD tends to 0, then you are going to get MMD k of Pn P tends to 0, then Pn tends to P. So in a way, if the MMD goes to 0, then the P and Q will get close to each other. And so convergence in distribution, if and only if we have convergence in MMD. So its advantage is that it is an integral probability metric that can be computed directly from data without having to estimate the density as an intermediate step. So you see here, this is like consistent with the idea that I was talking about at the beginning, is that we don't. So here, I mean, a lot of techniques. I mean, if you want if you want to do data, what you do is that you compute first you estimate first the density from data, and then you apply statistical tools. And then here the idea of what I'm talking about is, in a way, we want to develop results or theorems where you don't necessarily have to learn the dynamics. I mean, of course, I mean, it will help to learn a dynamical system from data, but this shouldn't be necessarily always the objective. I mean, the objective is always what are the questions that you are asking, and on which kind of quantities that you are trying to compute from data. And yeah, learning the dynamics, or the in the case of a deterministic system, or learning the density, for example, if you are dealing with probabilities, is not necessarily always the best shot to do, because it will create an intermediary step that may come with its problems. Yeah. So the MMD, for example, I mean, as I said, it's a metric that you can compute the metric directly from data without estimating the density as an intermediate step. And then unbiased estimator is given by the following. So all you have to do is that you have your data from P and Q, and then you compute this quantity here, and this will give you a measure of discrepancy. As I said, yeah, so for example, one of the things that you can look here at is for example, if you use the linear kernel, then you are going to end up having a change of means. But then if you have the Gaussian kernel, then in a way you are looking at the changes of all the moments, because if you expand the Gaussian kernel into Taylor series, then you are going to get the X. So the difference between the linear terms will give you the difference between the means. And then if you go to the second quadratic term, it will be related to the variance. And then the second moment, the third cubic term is the third moment, etc. And so if you use a Gaussian kernel, in a way you are keeping track of all the changes at all the moments. I mean, that's one way of looking at it if you are using, for example, the Gaussian kernel. And this is why the MMD in that sense is powerful one, and because you'll be able to track all the different statistics. Yeah, so now we move to the main question of what is a good producing kernel Hilbert space, especially if you are dealing with a given question. So this is what the method of kernel flows is about. So yeah, so we already looked at the problem of learning an unknown function from random samples, and we said that yeah, there is a need to regularize if we want to make things easy to compute. but you see that regularizer has an RKHS norm that depends on the RKHS. So it has been proven that, yeah, so that this problem, which like ill-posed, becomes well-posed in the context of optimal recovery, where by just working in a certain Banach space with the following norm and identifying the problem as an optimal recovery problem as the following min-max error, yeah, practically, I mean, what this is about, I mean, the main premise here is that the kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. So that's the main way of looking at what it means to have a kernel, a good kernel. So in my talk in about 3 weeks, I will show that actually this should be the way of looking at how to choose the proper RKHS. And so I'll make a link with compression and Kolmogorov complexity. So I would like to argue, again, it's more of exploratory thing, but I would like to argue that this is like the right way of looking at how to choose the right kernel and the right RKHS by considering complexity and compression, and this is what we see here, because we are saying that the kernel is good if there is no significant loss in accuracy in the prediction error if we reduce the number of points that we are using. So here, I mean, this led to the introduction of this relative error, so which is the value of the interpolant with capital N points versus the value of the interpolant with capital N over 2 points. But I mean, again, I mean, don't focus too much on the capital N over 2, and in a way, so it's really about reducing the number of data that we are using for interpolation. So so if we have a kernel, then you already see if you are looking at the representer theorem. So here it will be parameterized with capital N, parameterized with theta with capital N points, parameterized with theta with capital N over 2 points. And so this relative error will be written as follows. And the algorithm will run as follows as well. So if you have a lot of data, and what you are going to get is that first you are going to take first like a subsample of size n, and then a subsample of size n over 2 and then you construct this metric, which is the values of y's, and then the value, so the k is the kernel covariance matrix with capital N over 2 points, and this is the numerator. The denominator is with capital N points, so this will be parameterized by theta, and the goal is to reduce the rho, which is, as I said, is the in a way, like you can see it as a measure of compression, and then you run theta, evolve theta in the gradient descent. So you are going to get theta k plus 1 is equal to theta k minus delta gradient of rho with respect to theta. I mean, here I like saying that this, in a way, so this is also like a trainable machine learning method. So we talk about like training in machine learning. So there is a way to do also training for kernel methods. But when you are choosing, you're looking for the right kernel, but it's like a training, but trainable machine learning method that is not a neural network. So we have tendency to think that training happens only when we are dealing with neural networks. But yeah, you see here that we can also have kernel methods that can be trained because we are looking for the right kernel and the right RKSS.
Permitting,
Yes.
we are also assuming that the kernel is differentiable with respect to the parameter theta, right?
Yeah, that's correct. Yeah, exactly. Yeah, yes. So here, then we applied this to a problem of learning dynamical systems, where we have a time series x1 to xn, and our goal is to forecast xn plus 1 based on x1 to xn. So we start first working under the assumption that this time series can be approximated by a solution of dynamical system of the following form: zk plus 1 is equal to f dagger zk to zk minus tau dagger plus 1, where tau dagger and f dagger may be unknown. So yeah, I'll skip the question of how to find tau dagger from data. I mean, you can look at the paper, but there are many other methods that people have been looking at, which is the time delay embedding. And yeah, so here we are just going to reformulate our problem as the problem that we looked at the beginning, which is the problem of learning an unknown function from random samples, where here yk is xk plus 1, which is a zk plus 1, and xk is the past. So we want to predict the future based on the past. So from what we said before, we already have a closed form solution to that problem, which is k little x capital X, k capital X minus 1 times y. So this gives us the following f. But here I would like to step back a little bit, because remember, we said that we are not necessarily always learning a function or learning the dynamical system when we are asking questions about dynamical system theory. So I mean, there is a difference between questions in dynamical system theory and about learning the dynamical system from data. And so this is what led to introducing different variants of kernel flows. In a way, I mean, what we want to do is you want to choose the right kernel based on the right question that you are asking. So this one, for example, the one we just talked about, which is the relative error, is the metric associated to the RKHS norm, is about like having like short-term predictions. But like in dynamical system theory, it's not always about predicting the future, but we also have like qualitative questions. For example, if you want to have the long-term behavior, then I mean, usually what comes to mind are the Lyapunov exponents. So here we are going to say that a kernel is good if the estimate of the maximal Lyapunov exponent based on capital N point doesn't change much if we use capital N over 2 points. So, or we can also use other Lyapunov exponents. So this, in a way, this is about first one is about short-term prediction. The other one is about like long-term behavior. Then here, another one is that we'll say that the kernel is good if the MMD between two subsamples of the time series doesn't change. But so we want to minimize this metric. So here, in a way, it's a measure of statistical dependency. And here I still didn't prove it, but my intuition is it's probably related to the Frobenius Perron operator. We are looking at the evolution of statistics. We start up with probability distribution of the initial conditions, and then you move it forward. And in a way, so this rho MMD is also talking about this kind of statistical behavior. And the last one, I mean, is about the attractor. So if you have a chaotic dynamical system with an attractor, so we like to argue that, yeah, good kernel in that case is that the Hausdorff metric between the estimate of the attractor with capital N points versus capital N over 2 points doesn't change much. I mean, and these are like different ways of learning the kernel for this kind of problems. So so there are like two ways where we looked at this kind of problems. First, we started looking at the toy models in dynamical systems, like the Bernoulli, Henon, and Lorentz. And the idea there was try to find a kernel that allows to deal with these toy models. And so yeah, so I came up with this kind of relatively simple kernel. I mean, Gaussian kernel is like a universal kernel, but then you also want to look at patterns. So this is like one of the other things here is that when we are dealing with like learning a dynamical system, it's not necessarily learning the right-hand side. It's really about learning the qualitative behavior and the patterns that are present in the system. So for example, in the case of the Bernoulli map, xk plus 1 is equal to 2xk mod 1. So it's not necessarily that you just have to find a kernel like a 2xy mod 1 or something like this. You need to be able also to be to try to uncover the underlying dynamics. So yeah, so I thought that this would be like good example to crack. But it wasn't easy initially to find the kernel, but then I remember that this was related to the tent map through transformations, and this is how I end up adding the triangular kernel. So you see, I was trying to, as I said, I wanted to look at the simplest hard problems in dynamics. And so one of them was to try to crack the Bernoulli map. So it wasn't easy at the beginning, but then by just adding this triangular kernel, things became easier. And also, this is like the locally periodic kernel that allows also to detect locally periodic behavior. So you see, I mean, this worked quite well. I mean, see, for example, here, second figure is that when you don't learn the kernel, and the first figure is when you learn the kernel. And yeah, for this kind of initial condition, and for different initial conditions, you got the third figure here. Lawrence. So you already have, yeah, so here this is like a very popular system. So here you also use the similar kernel. We have the X, Y, Z, and these are the true versus approximation. These are the errors. Red is after learning the kernel and green is before learning the kernel. So you see the error is is reduced. And also remember, we also want to learn the long-term behavior and attractor. So here you see the reconstruction of the attractor. First, third, and fifth is after learning the kernel. Second, 4, and 6 is before learning the kernel. And this is in 3D. So left is after learning the kernel, and then right is before learning the kernel. Yeah, then when we uploaded this paper on the archive, someone from the Argonne National Lab approached us, and he said, yeah, that let's try to work this in like through a real example that they have like weather data from weather prediction, and so they have like real data sets, and they have also two PDE models that they are running on their supercomputers at Argonne. So one is called the HiCom, and the other one is CASM. And yeah, so you see, they already have like neural networks and LSTM. So in their computers, so one of them is the method is taking 800 core hours to forecast on this on Cray XC40 system. CSM 17 million core hours on this Yellowstone for the one of the other methods. And then LSTM is 3 hours of hold time on this data supercomputer. And then using our methods, using kernel flows, and just a kernel, simple kernel with I think 20 or 21 parameters. Yes, it was 40 seconds of training, and you see the results are not that bad. You see this is the true is the red with satellite. Green and orange are the two PDE models, and the kernel flows on the laptop is the blue one. Yeah, so that's you see the performance is quite good. And yeah, one of the also the objectives here is also, you see, when you are dealing with kernel methods, is also to reduce the number of parameters. So you see here, as I said, the kernel was only 21 parameters. But if you are dealing with a neural network, you see how first you have to deal with the choice of the architecture, and usually the number of neurons that you are having, the number of layers, then so all the parameters or the weights that you have to introduce. So one of the advantages of kernel method as well is that you are not using a lot of parameters, and you see the performance is not that bad. I mean, with like for 20 a kernel with 21 parameters trained using kernel flows is doing as good as complicated neural networks run on supercomputers. So that's for the short term, and then for the long term, yeah. So also this like a global weather prediction. You see, so we remember. So in dynamics, again, it's not about just like time. So dynamical systems is not only about like time series prediction, right? So there are like a lot of other questions that you can ask in dynamical system theory. I mean, here, for example, when it comes to weather, we also want to see if we have a global performance, and you see that's the similar kind of things. I mean, like, this is true via satellite, kernel flows, HiCom, and CSEM. And yeah, so we were told that this is also good because we were able to detect some some patterns here on the I forgot the name of, I think it was like an Enzo cycle or something like that. So anyways, it was like also something that was acceptable to them, yeah. So the other problem is the problem of learning partially observed dynamical systems, where you assume that you don't know, you don't have access to all the states. So you have only access to a state of dimension n, but you don't have access to the other components. So kernel methods can handle this by just like also reformulating the kind of problems that you are dealing with. So you just like reformulate the minimizer and then derive a representer theorem for this kind of problems where you have parts of the state is not observed. So this is like so this is the representer theorem in that case. So the first component, second one, and then you just learn minimize with respect to b, which is the second variable that is missing in that case. I mean, remember that one of the things in the representative theorem, you always need the y component, but here you see part of the y is not known, so you need to estimate the other part of the y by finding a good minimizer. Yeah. So this worked well for the case of Lorentz. So we assume that we have access to the xy, but not z. But we also looked at the problem of only x and learn y and z. So one of the things here, I mean, what I noticed is that you have first you have to increase the number of parameters in the kernel, and also increase the time delay. So before it was 3 when you had like full information, and then it became 4 when you have like partial information. But still, it was okay. I mean, you see, so this is the x, y, z, true versus approximation, and these are the errors. And this is the attractor true, which is blue versus approximation in is red. Yeah, so you see, so as I said, we have like two ways of looking at the kernel. So one is the bottom to top, where you try to build the kernel by hand, which for different toy models in dynamics, and then you sum them up, and then you see if you can deploy them, and then work on a complicated system. So here we want to do it the other way around, where we say, okay, assume that you have like a dictionary of kernels. So just like choose in a way, all the kernels that you can put in a computer, and then you sum them up, and then you throw a weight. So you have theta I square ki xy beta. And then we want to sparsify this kernel. So we add an L1 penalty term on the theta, which are the coefficients. And then our goal is to zero the maximum number of coefficients in the theta. So apply this to a large database of, so initially it was 131, and then we moved to 133. So we had like 2 papers on this kind of problems, where we used 2 different metrics, and this is 131, and the other one, I mean, I think now it's what 135 chaotic systems. So our goal again is to find one kernel that you can use to learn an entire family of dynamical systems at once. Yeah, but I mean, see, when you sparsify, what's going to happen is that the terms that become 0 are not going to be the same for all of them. Depending on the system, some terms will become 0, other terms will become will remain non-zero, but it's not always the same terms that are 0 that are going to be 0, but at least it will be the same in a way, the same mother kernel that allows to tackle the whole family of systems. So that's the kernel. It has like 40 parameters and 15 terms. So yeah, so as I said, the idea here is not necessarily to learn the right-hand side, right? I mean, this, for example, when you have like people who deal with Cindy, and then they try to learn the right-hand side, and then they say, oh, okay, it's not really working if I am having given dynamic systems. I mean, I think this is one of the key take-home messages from this talk as well, is that when you are learning a dynamical system, remember that it's not always about learning the right-hand side. So because you really want to learn the pattern, the dynamical systems is not just so you don't learn basically a dynamical system in the same way that you learn a function. So it's not about function approximation. You are also trying to learn the dynamics and the qualitative behavior and the patterns. I mean, this is why you have this kind of kernels on the right-hand side, even though, I mean, they don't necessarily appear on the right-hand side of the dynamical system, But if you use this kernel to learn the dynamics, then you are able to mimic the qualitative behavior.
May I ask a question here?
Yes.
Since, you said that you applied to 131 chaotic systems, and is in between also the climate change such that although climate change for me is not so chaotic, maybe has certain rules, maybe. But this is, I wonder if it is, if you apply to the climate change also, that's what.
Yeah. So this kernel, we didn't apply it to the weather thing because this is like so the weather, we use a different kernel, but it was less. It was only 21 parameters. Yeah, but it was inspired. It was before actually we got this idea of sparsification. Right. It will be worth actually applying this and see what happens to the weather thing.
May not be so chaotic, maybe also because it has certain rules also.
Yeah, exactly. Yeah. This I don't know. I mean, this is a very good question. Yes, I don't know how this will perform with the weather prediction, but yeah, but it's worth. I mean, if I find a good student, I'll probably ask him to do that.
Like precision, such things, they have also certain rules, not so chaotic, maybe.
Yeah, exactly. Yeah, possibly, exactly. Yeah, you are right. Yeah.
Thank you.
Yeah, and so these are an example here. For example, like 3D system from chemistry. Yeah, okay. I mean, I don't. Yeah, there's a problem here with the figure, but anyway, so the bottom line is that we are able to recover the attractor, and same for this electrical system. So the advantage of this library is that you are dealing with like different systems from different fields. I mean, this is one of the advantages of that library is that it has like electrical engineering, chemical engineering, astronomical models, and these kind of things.
In this library, apart from the continuous dynamics, there are also discrete dynamics. Am I right?
Yeah, I think it's mixed, exactly. It has like a different,
Okay.
it has everything. Yeah, but that's also like a good question here because in practice, we are going to discretize anyway, right? Because you are, at the very moment you are running your code on a computer, so you need to discretize. Yeah, so this is also one of the points here is that, when we deal with
The good thing is that your kernel already parameterizes whether you are in the discrete case or continuous case. It doesn't matter when you have the collection of those multiplication of the kernels and then the addition of the kernels will also distinguish between the continuous and the discrete dynamics.
Yeah, exactly. Yeah. So that's so here, for example, this is what you see here, for example. So applied actually to, as I said, remember, we applied for example, two metrics to measure. For example, this map is for the short term and the Hausdorff distance is for the long term, and then attractor reconstruction. And you see like with regular kernel flows, so the error is the -3. With sparse kernel flows is -10 to the power -5. With when it comes to attractor reconstruction, the Hausdorff distance between true versus approximation is 278, and this one is 10 to the power -2. For the electronic, it's 610 -2, 0.004 SMAPE, and Hausdorff is 12 versus 0.2. And I said we also looked at the Hausdorff metric kernel flows, sparse kernel flows. Well, here you change actually the first term, so it's no longer short term, but you also you look at the Hausdorff distance between the approximant of the attractor with the capital N pounds versus capital N over 2 plus the regularizer. So apply it to the database. I think here this is where the students applied it to 133. So I think this is like 133. And you see it works well. I mean, here I have like regular kernel flows, sparse kernel flows, Hausdorff distance regular kernel flows, and Hausdorff distance sparse kernel flows. And these are projections of the attractors. So statistically for the, so here exactly, so this was like 133 systems. So statistically, I mean, you see that Hausdorff distance sparse kernel flows is better performance with whether we are dealing with short term or long term and attractor reconstruction. But it's not always the case. I said like on average is doing much better, but for some systems, I mean, other versions of kernel flows are doing better, but on average for the 133 system, this is what we call like that positive distance sparse kernel flows is doing better, both short term and long term. And yeah, so the other part, sorry, I think, am I running out of time or so? Do I have like, is it like 5 minutes left?
Oh, actually, we don't generally have time restrictions. Sometimes we go
Ah.
on, but of course, we can leave some of the parts to your next lecture on the December something, the first week of December we have arranged. If you also would
Yeah,
like
can I
to,
just like finish this? Yeah, but
yeah,
again,
sure, sure, you can continue.
Yeah. So in 3 weeks, I will be talking about algorithmic information theory point of view on it's a totally different kind of problems. Yeah, but if you want, it's up to you. If you want me to continue, or I can have like another third talk where I start from here, or as you want.
That's your choice. Let's see, since we are more than 45 minutes, so maybe if it is possible, I will take the questions then.
Okay. Yeah. Sounds
So we
good.
can continue next time.
Yeah.
Maybe
Yeah, okay, let me just go
we
quickly.
can change the title of your next talk.
Yeah.
Depends on you, actually.
Yeah. Okay. Yeah, we can just call the same title and then part 2 or something. Yeah. Yeah. Okay. Let's just go and to the conclusion, and then we can I can start from here next time. Yeah. Yeah. Okay. So yeah, for today, I mean, I covered different variants of kernel flows and then how it helps to approximate chaotic dynamical systems. Yeah. So next time, hopefully, like maybe maybe either in 3 weeks or maybe like later on.
Yeah,
Because in 3 weeks I wanted to do to talk about something else because this will be like totally different slides. But here, so maybe in the next, the second part of this talk will be about detecting critical transitions in SDEs, and also about the center manifold theorem and construction of Lyapunov functions from data, and then possibly other things, because we also have like a global version of kernel flows where we use kernel methods to find global optimizers. I mean, anyway, so there is more stuff to work on. But again, the idea here is that in a way I'm adopting an inductive argument. So I'm not doing something deductive, but inductive. But the main story is that the main message is that working in reproducing kernel Hilbert spaces offers tools for a database theory of dynamical systems. So that working in RKHS is the right mathematical, seems to be like the right mathematical framework for developing a database theory of nonlinear dynamics. So these are some of the papers that you can find on Archive and ResearchGate. And I like advertising for the, yes, I'm currently co-editing special issue on machine learning and dynamical systems in Physica D. So yeah, as Omar mentioned before, so I'm running a seminar on machine learning and dynamical systems. You are welcome to join the mailing list, and then yeah, you're welcome to ask me questions. Yeah, thank you. Yeah.
Thank you. Thank you very much, Boumediene, for your nice talk and information on not only machine learning, but especially focusing on the reproducing kernel Hilbert space. So I wish our audience, if there are some questions, comments for the talk. Bülent Hocam, your microphone is not.
My question is, how do you choose now this year this strange kernel with signs, exponentials, and polynomials? What is now the idea behind it?
Yeah, so here, as I said, yeah, so that was one of the main questions that led me to propose this method of sparse kernel flows, right? I mean, the idea there is that is exactly that. How do you find the base kernel, and then sparse kernel flow is telling you actually you shouldn't. I mean, you don't have to worry about what's behind. You just have to sum the different kernels that you can find online, and then you just sum them up. But as I said, I mean, for me, what I consider to be the underlying principle is really to detect the patterns. So you are not learning necessarily the right-hand side of the dynamics, but really in view of learning, for example, the attractor, you are trying to reconstruct an attractor, a good attractor from the data. You are also trying to minimize these kind of errors, like the short term versus long term, and other metrics that you may be interested in the dynamics. Yeah, but there isn't. I mean, there isn't. For me, I can give you, as I said, an explanation for how I started thinking initially about these kind of problems. So I said, so I know that the Gaussian kernel is universal.
Gaussian. This is
Is the
Gaussian.
Yeah, that's the Gaussian kernel. Yeah, so this is I started with this,
The
but then
next is as a Gaussian too.
yeah, this is Laplace because there is no two here. You see?
Okay. This is it. This is Laplace. Okay.
Yeah, that's Laplace kernel. This is quadratic kernel, like just to add.
Okay.
And this is the locally periodic kernel in order to be able to detect locally periodic patterns. And so this one, as I said, is the triangular kernel. And for me, that was in a way, that was the game.
That's an azimuth kernel, or
What it is?
this, or not?
Triangular kernel.
The hat function.
Yeah, the hat function, exactly. Yeah. And this is for me. I thought about it because I thought as I said, I wanted to crack Bernoulli as a start. I said if I'm able to do something useful, then it should be able to. I have to find a kernel that allows to deal with Bernoulli map, because there is a lot of work on learning Lorentz, but I mean, there are so many methods on learning the Lorentz, etc. Then you say, okay, if I come with Lorentz, it will not have a higher impact, and then it will not necessarily solve all the complex problems in dynamics. But if I do Bernoulli, then it can be viewed as a good toy model for like many of the phenomena in dynamics. But then you see, if you add in with xk plus 1 is equal to 2xk mod 1, then the first question is, okay, how are you going to find a kernel for that? So it's not obvious which kind of kernel that you are going to use. It's not like you are having xk plus 1 is equal to x squared, and say, okay, x squared, I'm just going to use x minus y square as a reproducing kernel. Yeah, so here so this one, I thought, I started thinking more about what is the Bernoulli map, and then you think that it's like, okay, directly related to the tent map, and then at the very moment I saw the tent map, I said, okay, tent map, you have a triangular kernel, and this is how I end up adding the triangular kernel. Yeah. So in a way, this, as I said, it was very hand wavy at the beginning, but then I said, so that this cannot be like a good approach to solve complicated problems. And this is what led to do it the other way around, where I said, oh no, let's just do it the other way around, where you go take a database of all the kernels. So you can go online and look for the kernel cookbook by I forgot his name, from Toronto. So it has like an entire large dictionary of kernels. So I thought, okay, let's just like sum of them up.
Gregory, I guess.
What is it?
Gregory.
Okay.
Or Michael McCourt.
Yeah.
One of them, I guess. But anyway, I was wondering, since you have mentioned the Lorentz equations, those triangular kernel also has given you the, I mean, how well these kernels worked on defining the Lorentz map when you were working on the Lorentz equation.
Yes, it was the same system actually that I applied for Lorentz. Yes, I did well. So
that coefficient was the highest one, I guess.
Yes. You are talking about the coefficients. Yeah, I don't know actually. You are right. I mean, this might be worth actually exploring what happens to
the since especially in the partial data when you don't have the z values.
That's a very good question. Yeah, this I didn't actually. All I know is I said we had to include this, I had to add extra terms, so it was this 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, nine kernels and total of 22 parameters. Yeah, but you are right. I mean, it may be worth looking at the size of the coefficients.
Yeah, especially for the Z values.
Yeah. That's a very good question. Yeah, I don't know actually, but it's definitely a good question. Yeah.
Because we are generally approximating that Lorentz map by tent map, right?
Yeah. That's a good question. Yeah. What we looked at is really what I said is the thing is how the coefficients are becoming zero. For example, you see, I forgot actually to talk about it, which is here, for example, for the chemical system, you see two coefficients became zero, like theta 7 and theta 13. For the electrical engineering system, it was the theta 8 that became zero. Yeah, but it may be worth looking at. Yeah, you are right. I mean, it may be worth looking at the size of the coefficients. Yeah, but definitely you see, for example, here it's 7, 0, 1. I mean, there's definitely more weight on certain coefficients than others. Yeah. So here, I think for this multi-Chua, yeah, they all seem to be around. Yeah, you see 1, 0, 9. Okay, you have 0, 2 here. 1.8. Yeah. So I think that's a question worth exploring. Yeah. You are right. Yeah. What is the size of the coefficients? Yeah.
Thank you.
And my question is, for example, if you have an Hamiltonian system which is not chaotic and which is now integrable, do you use the same kernels with the parameters or something different?
Yeah. So this actually, we are working on learning Hamiltonian systems now, and we are trying to learn. We are using this kernel. Yeah. So we are actually using this approach, the same kernel, and then the sparse kernel flow. So exactly this approach. We have a sum up different coefficients, and then we do a sparsification. But we are starting with this kernel. Yeah. So
but you can use, for example, the Gaussian kernel, and you write in an asymplectic form, and then you have a symplectic Gaussian kernel, and that will be enough, I think. Only one kernel. You don't need all the parameters.
Yeah. So we still don't. Yeah, as I said, we still didn't crack Hamiltonian system, so we are still working on it. Yeah. So maybe like a next time when my next talk we'll have some results, but so far we didn't.
Which is now satisfying this symplecticness property, Gaussian kernel spatial kind of this, then you can modify and then see, and it works. And then you don't need maybe now then.
Yeah. That's good idea. Yeah.
But that lasso regression, where the sparsity comes from the one norm of theta, will just a little work actually. So it won't be a too complicated problem. The correct kernel will appear based on the coefficients theta. So it doesn't matter whether you have pre-knowledge or not. The same is true when you specify, I guess, for the distributions, you don't need the prior and posterior distributions. You start with a kernel, and whatever the kernel is obtained, then the posterior will be out of this kernel. So you don't need to have a pre-knowledge of what the dynamic is. The data will find its, or the kernel will find its way through
Exactly.
data.
Yeah, exactly. That was the idea. The idea is that the data will take you, will discover the structure. I mean, that this is you give it everything, and then it will tell you a thing. But yeah, but maybe it may be worth actually exploring this idea of like in a way like symplecticizing the Gaussian kernel. So maybe add it as an extra term, the symplectic Gaussian kernel, add it as another term in the library, and then see if sparse kernel flows will converge to it and give it like a higher coefficient. Yeah, that's a good idea. Yeah. But that's the whole idea of sparse kernel flows, is that you give it like a lot of terms, and then in principle you are going to converge to a kernel that will be good enough for your objective. Yeah.
Okay, thank you. Is there any other question? Okay, there seems no other question. So I will end this part of your talk, therefore.
Yeah, okay.
And we will meet for the next one. So you can write me later on about if there is a change in the title and maybe the small
I
abstract.
think we, yeah. Okay, yeah, I think we'll just
And
keep this because we are talking about like learning kernels. And then the next talk is about what it means to learn kernels from the point of view of kernel level complexity. And then maybe like a third talk will be about continuing this talk, because I think it's nice to, because we stopped in a way at the right point, which is like,
okay.
what does it mean to learn a kernel? And then, I mean, sorry, how to learn a kernel? And then next time will be, okay, what does it mean to learn a kernel? Yeah. So I think we just
So,
keep things as they are, and then maybe a third talk will be about part 2 of this talk, and maybe I'll add other recent results about global kernel flows. Yeah.
One more
I say thank you very much.
question.
Yeah, sure.
Yes, Aziz Hocam.
Just one more question I want to
Yes,
ask.
yes.
That's what. Yeah, because in the here, all the events that we observe, very little of them are very deterministic. All are quantic. Here, I think it seems that very good method to apply to many problems. Maybe and one is that climate that change. The other also there are everything is probabilistic, not deterministic. So it is very applicable and very good method. And we thank you really for introducing such methods again. So that it is very interesting and very useful, I think.
Yeah. Thank you for coming. Yeah, thanks again. Yeah.
We also wish to thank. So, dear Professor, we are generally putting those slides on our website and also the record. So I don't know whether I will get the record on my
I
Zoom
will send
account.
yeah.
So you can just trim the video if you like, or trim also the slides for this talk. We can also share with other audience, because I know that there are some professors that have mailed me yesterday that they are not going to be able to come, and they asked me for the recording. Especially.
No, I usually make my talk public, and then I'm happy to share the slides. I'm always like looking for collaborators. So whenever I can get like more collaborators, then I'll be happy.
Thank you very much. So we are also
going to. Did I
going
send you the slides or not yet? Did I send you the slides or no?
No.
Yeah. Okay.
Not
Yes.
yet. This is the first
Okay.
time
So I'll
that
send
I
you the
see.
slides, and you can put them on the website. Yeah. No problem.
Okay, I will put the slides on our server, and also we are going to publish your talk on our YouTube channel, I think Institute of Applied Mathematics channel,
Right.
and especially there is a series under RKHS seminars.
Yeah. That's. Yeah.
So we will also publish that
All right. Okay.
video recording that you
Yeah.
sent to me.
Yeah. Sounds
Just
good.
if you want to, generally we share those in the raw format, but if you want to cut some places,
So maybe I'll
you are welcome.
cut the first 5 minutes because I think it was like empty somehow. Yeah. I mean, we were just like talking.
It really doesn't matter.
Okay. Yeah. Then it's up to you. I mean, I personally, I'm just going to send you the link, and
Okay.
then you can trim if you
No,
want.
we will just put it just exactly in the raw format.
Yeah. Okay. Yeah, I do the same because I don't like having that. I think mathematics are lazy.
Yeah, mathematicians are lazy.
Yeah, exactly.
So
Okay.
Thank you very much, and I thank you all of the audiences, and they are starting to leaving.
Yeah, exactly. Yeah.
So we thank you very much for your nice talk.